Okay. Hello. So, hello guys. I'm sorry for the technical. We're supposed to start like 15 minutes ago, but some technicality. But anyway, so today's we will be exploring. Let me just fix something first, and then we can keep going. Where are you? Okay. All right. So. Thank you again for joining. So today we will be doing continuing with what we had before. So the last stream we were going through the debugging process, and then we found something interesting that is happening in the in the code. But before that, let me just give people some context. So if you're familiar with the ARC prize. So this is an interesting prize for benchmarking how AI systems will perform well on tasks that usually are well performed by humans. So our goal is to, first of all, the goal we have two goals. The first goal is to just have a model that works, that it does what it's supposed to do, and then once we have such a thing, a system that can run in any environment, then we can test bed the model in an environment where CA is CA by CA I mean cellular automata. So cellular automata is it's a famous uh, computer program um, that uses some sort of rules, like uh, usually like they are simple rules, they are not complex rules. And we can also discuss this once we have a very stable system that can run in any environment. But for those who are not familiar with CA, you can check out cellular automata and read about cellular automata and what they are, where they originated, and also check out the Game of Life. And I think my internet is misbehaving again. Okay. Oh, that's not good. All right. So, yes, check out CA, check out cellular automata, and read about what they are and how they can be used in any any system or any problem solving stuff. And yeah, so the goal is to use cellular automata as a test bed for our model. Once we have a model ready that can run in any environment, then we can use a cellular automata as the test bed. But for that to happen, we need to fix this guy. So this is what we will be doing today. And I just for those who are not with us uh, yesterday, was it yesterday? Just run you through the what we found. So we printed a few parameters. So the x is the sensation. The sensation is what the model is sensing at the current step. And then what tx is the tensor, just convert that to tensor. And ty is so y is what we predict. So this is the predicted the predicted value. So from X, you predict what the model will see next. And so the Y predict is this. And so from what you can see, this is so X are like below what we want. They are like 0 point something something, and Y is where is Y? Y is crazy. So this is what causing the bug. So the prediction is quite high. It's predicting with values that are really high of the bed. So we want to figure out why the prediction is doing that, and this is causing the coherent value to go to zero because we're doing something like let's see. So I need to open this code first. Go to yeah. So coherent. So this is the coherent. So we are performing. We're getting the mean squared error. So the mean squared error is the dot function of the dot from the dot function of the residual. The residual is just the observed value minus the predicted value, and then you get the residual. So if you get such values like this, so if y looks like this, and you are doing something like x minus y just gives you a large negative value. So if this is y, then x minus y will just be a large negative value, and then you perform this dot function on that. So say this is r squared. So r squared, if you have 500 as the sorry if you yeah say you have 500 as y, the residual, and then you do or you have a minus 500 as the residual, then you do something like r squared, then what you're getting is 2500 25 is it 25,000. You're getting a big value. And to if mean squared error is a large enough value, then what you when you do an exponential of minus zero point 0.5 times the mean squared error, you get something minus something. So that's something. If mean squared error is a large number, then exponential of a large value is just it's just zero. Like it under what's the word? It gets to a value where we cannot really. I mean, exponential of a large value is just it just shoots to zero. So we get a coherent as zero. So that's why we hit every time we do a debug or a print of this, we get something that we get coherent to zero. That's because mean squared error is large, and y predict is blowing up. So this is the reason. So if this is if the prediction is crazy, then what you get is coherent just goes to zero, it just blows up to zero. Now, why is this going to a large value? So that's what we want to figure out. Now, I've made some prints right here to just show you that this is happening in a richer environment. So I think let me just open this. We have so the minimum. So this is what we were running the model on. So this is the richer environment, and we set richer. We did have richer somewhere. Yeah. So this is richer. So what we want to know is why is it happening in richer and not the toy version? Now I want to do some tests. Just to show you that it's happening on the richer environment. So the first thing I will do is, because we already have a print, so we want to just see the values, how, x and y as they as the model trains. We will do this for a few steps so that we don't. So I would take this example. This is the configuration file which has no reader. It's just this is the toy version and no return, no nothing else interesting on that environment. So we will when you do this, so it will train do what it's doing, but all if you check the X and Y, it's really just it's not blowing up. It's never going higher than a value um, that might lead to mean squared error blowing up. So we will um, let's just see what happens. Okay. So these are prints. Nothing interesting. Just printing X and Y. X is the observed the sense, the current sense in the time. So if um so if let's see, so this is what is the model is sensing at this specific time, and then this is what it's predicting. So it just y and x, and let's see what happens. So for Richa, we expect it to be successful. It will never hit zero. So the debugger will not never be reached for toy the toy version. So this is the toy version, and then we will do another run. Let me just maybe I can do this, two runs at the same time. Hopefully, it doesn't. For this, I will use this configuration. So the configuration is 7A Richa. Richa is turned on. And yeah, I think this is the minimum. The minimum. Oh, I see. I cannot do this. Oh, I see. Wait a minute. Oh, I see. I think I need to do something like 7. Yeah. And when directory to be 32, so we don't override what is being done by the toy version. Okay. Uh, all right. So we execute these. Let's see. Now I'm running those. Okay. So this is way ahead of time, but we will see that with Richa, we start to see large values in the training process. We will see large values. So by what those large values are, large value, specifically large values for Y predict, and those values just tells us that our predictor is wrong. Actually, it's not right, but the system just does it. It notices that it's a different kind of environment because richer is it's kind of a real environment, but our toy version is a latent, it's a hidden environment. We set the parameters and manually. We set the environment manually ourselves. So that's why it's latent. And then once we put the model inside a real world, a real environment, like Richa, it just starts to do crazy stuff. So we hit the debugger. That's because coherent got to 0. And when you look at these values, they start to get higher. Yeah, I don't know why. Okay, so let's see why. So why here is it's not so high, but 6 is still high. 6 is also 7 is high. And when we run this again, I think we will get and a much different value, a much larger value. Like yesterday we did and got something like this. This is a lot. This is like for 422,000. That's a lot of that's a huge number, right? So, and when you look at the other side, is this is the toy version. Never hit the debugger. So the coherent is just okay, it's doing fine in the toy version. But then in the real world, it just blows up. Coherent goes to zero. Now, what we want to do now is to try and figure out why we would just go to because we know the issue isn't in the coherent function. Coherent just does what it's told to, like it's doing its job. But when what we pass into coherent is what we want to find out why it's failing. So the the so this tells us the predictor is the model is not predicting so well. And we will just let me go to the where we're getting these values. So coherent is we're getting the values from this. So x next is the next observation, the next sense, sorry, the next sense, and then y next is the next predicted sense. So by so this is coming from focused, but we don't want to. Do we want to look at focus? I think we want to look at realized coherence, which is in the kernel. And yeah, so here we want to look at realized coherence. This is the y predict, and this is the x, the current sense. And let's see. So predictor. So predict with variance. This is where the predictor is failing. So this is trying to predict what y will look like. So what we want to do is figure out why it's not working from this guy. From where is predictor? Okay, right here. So so why does this return huge values? Now I we can try using predict. I don't know. This is predict variance, but still, it doesn't make sense when we if whether we try predict, because predict is just a simpler version of predict with variance. So if we try, let's see, I want to see what this looks like every time we do a print. So um, I will try to do this first. Okay, I need to get the prints here to delete them. Coherence. So we don't see a lot of stuff. And now the predictor. All right. But it's interesting that the model doesn't perform really well in the real world. By real, I mean richer. And I want to do here is the variant, effective variance. Then we want to see, actually we want y, not effective variance, because y is coming from fused. Yeah, so I think we need to see this, and ideally what we will want variance by row. So okay, so I should mention that what we're using for predictor is RLS, and RLS is just let me where is the browser? Okay, see, RLS is what the function, the algorithm we're using for prediction, because a recursive mean squared error. Sorry, recursive least squared error. RLS, recursive. Um, so this algorithm is what we're using for our predictor, and once we feed it, it trains online. I need another. It's an online training algorithm. It's adaptive because we're building an adaptive predictor. So I think RLS is the best choice. I think we can think about other algorithms to use, but RLS is what we are using currently. And let me just show you the updates. So this is where it's doing the updates, and so it's the learning process online. As you train, it learns and adapts using the algorithm. But what happens is what happens when we have learned through the environment we are in, like the model is in a richer environment. What happens to why predict? So not predict well in this environment, but does well in a touch in a toy environment. Let's just see if we can try to figure out. So here we can see what y is, and we see this. And residual, if you do residual is, oh, sorry, where is this? R X R, um, where is it? TX TY. Right? I'm not in the right place. Okay, coherence, not here. Yeah, I think the debug hit the focused. Oh, I think we are in the focused coherence instead of this. So here we want to see what x and y is. So y next and y. Oh, I see. So y next is this, and current y is, wait, no, there is no y here. Oh, I see the problem. Let's continue. Mm, y just keeps going. What is coherent? Zero. It's still zero. Okay, coherent always zero. So I think we can't. 9. We're getting 9, 7. These are not so large like the ones we found yesterday, but okay. So let's get the print from the predictor. All right. So we want to run this, not the other one. Data 31, 32. Ah, skip 31. I'll make this 31 instead. All right. We we have started a new run. We just want to see. Hmm. Sometimes it gets to just zeros. No prediction prediction gets to just zeros. Okay, so this got too coherent. Now what is y? So y is still high. Now we know that it fails at this. Usually it's just 5. Once it gets to more than, is it more than 5 or 3? What is x is below. It's not. It ranges between 0.1, 0.0, 0.3, 0. Okay, let me see x. We have a function called x. Oh, 0.3. So the maximum of x, what about mean? Uh, minus point 0.4. So the minimum is minus 0.4. What about y? So y, we need to find out y is touch.max. So mean of y. Oh my God, that's bad. Where is it? Did I not see that? Uh, okay, I don't see it. I don't see 1,000, 4,000. Yes, the minimum is 4,000. Okay, what's the maximum for these? I don't understand. Why is this not? Oh, I see. Wait. No. This is times plus. Okay, it's still high. This is the highest value. The highest value for y. That's why it's blowing up. The highest value for y is 3,000. 3,000, I don't know, 3,400. Then the minimum, the lowest value is 4,200. Okay, minus 4,200. Okay. I see. I don't know. We can try to reduce the predict learning, right? And see if that's. Wait a minute. Oh, so this is let's go to par parovariance. What is happening? Parovariance. Clone to. Okay, I think that's helpful. Okay, let's go back. Fused. Why fused? It's being used. Also, we have Y fast. This is just how fast Y. Uh, predictor learns for I, and then y is slow, x, sorry, x. This is error fast, error low, error slow, just prediction errors for the fast learner and then the slow learner. Let's see. Okay. Oh, else. Okay, let's try this. Reduce learners rate, learning rate. I don't know. Let's try 5 or 0.3. Sure. Let's try 0.03 and see what happens. So this was the previous one was 34, 54 highest, and then this was minus 42, 25. And just change this to another value, 32. And see what happens. We need to hit the zero zero coherent. Oh, nice. There we hit. This is too large learning rate. Changed the learning rate, and now we get crazy amount of values. This is too bad. Touch. Oh, what's the maximum of these? Maximum of x is. Oh, okay, so x is fine. Like x is the minimum is -1, maximum is 1. X is the current sensation of the model. And this is quite big. This is 1.1 million. -1 million is the max. It has gone crazy. And 1 million. I don't know. Reducing the learning rate just makes it worse. Okay, let's see. Let's make it. Let's try 2.02 and okay, so 0.02. So the previous one was 1 million. Let's see what we get for the minimum and max. My internet is bad. I don't know if it's working. Oh, no way, no way, no way. No way. Okay. There you are. And let's see what happens to that mean for x. X is still okay. It's not that bad. Y. Okay, now we are at 102,000. What's the maximum? 113. Okay. Let me try something here. Let me clamp this to, let's give it, let's give it, let's say we just wanted to play around some value. Y, y clip or clamp, whatever you want to name it. Say we wanted to play around 5. So it doesn't go uh, over. Okay, so we had 5 in the previous. Did we have 5? I don't think we had 5. Okay, let's say we just wanted to play around 5. If it goes over 5, then it should never go over 5 anyways, because when it goes to such a large value like this, then mean squared error will definitely go to a large value. And we don't want mean squared error to go to a large value, because once that happens, it just doesn't allow coherence to keep keep the learning process going. The model stops learning is completely once mean squared error just goes to a large enough value, and that's not what we want. We can try to clamp this to a value that is slow. Maybe let's try this. Let's try. Okay, so hopefully I have this configuration into the predictor, and then predictor gets, we want the value project learning rate is fine. We also want this value to show up here. Let's say I want y clip. So okay, let me make it point a float value, and y clip or none. Should I make it or none? And init one predictor fig. Okay, we need this. Predict. Was it maybe 3, 5? Okay, awesome. Then I clip, I clip. Right, so this should be available. And our predictor. We can do it both for this. So this should be y. What we get from this is y predict. So I'll make this y, and maybe y is equals to this. Then I want to clip y into touch.clamp let's clap it to y to minus self dot y clip. We just want it to be within -5 and 5. If it's out of that range, then it will never be out of that range. Once we clip it, we just making sure the model still lands. It never breaks down. It always lands. And wait a minute. So this is why is this complaining? Self dot cannot access attribute. Oh wait, are you saying I don't have y clip? Oh, I see. I need to have it somewhere here. Self dot y clip. Okay, can you access it? Oh, come on, come on. It should be okay. Okay, say we will just if da 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 if self dot clip, then we do award. Jesus. Okay, self dot just set it to 5 anyways. If it doesn't exist, then we will just set it to 5. And we will do the same for y predict with variance. So we get y and then y dot touch clamp these to using self dot y clip. So this way, if it breaks down, then we know there must be something else. We have tried. Okay, we can keep learning rate as this. Maybe let's make it 3.0.3, 0.03, and keep the clamp. And then, so y should always be within our clamped value. So let's try these. First of all, let me clean these up. And 32, awesome, 32, remove these. And run again. Let's see. No way, I'm not printing anything. Oh no, I'm supposed to print something. Coherent. We need y. I need to see what y is. Mostly y, yeah, just y. All right, okay. Maybe a separation. I want to stop this training. And all right, so train again. We want to see what y looks like. It should always be, anyway, it should always be within that range. So the model will still learn, hopefully. Hopefully it still learns. Because it has been going crazy here. These values has been so high. All right, so hit a zero, hit a zero, hit a zero. hit to zero. Hopefully I'm streaming because I think my internet has been misbehaving right here. I don't know. This is not okay. 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 Still, stream is not working. Okay, how about this guy? Right, not charts. Oh, wait a minute. It worked. We didn't hit a zero. That's good. That's good. Let's see. Mathematica, where are you? Okay, that's interesting. See what happened. No way. We still got to zero somehow. No, 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 no. This is agent. Still got to zero. Or am I using the wrong one? Okay. This is up to 5,000. And this is up to, oh, I see. So we got to 5. It just plays at 5 forever and ever and ever. Oh no. Oh no. Okay. Okay. So I think system 2000. Okay, we can try another thing. Okay. Just stays at 5, minus 5 and 5. Where did it start? What about the learning rate? Let's try 2. Also, maybe let's try making these 3 and uh, 32. Maybe okay. Okay, let's try this first. But why does it say why does the plot say 0? It's to 0 somewhere. Okay, let's see. See if this works. My phone's still streaming, it's just loading stuff. Can't even see what's happening. Hmm. No charts. Oh no. So now it's three. It's stuck at three. Okay, so predictor prediction is not good. Coherent is 88. Okay, so what's mathematical saying here? 32 logs. And we're interested in coherent. Yeah, it fails way the steps are ahead. It's not at 2000. So once you change value of clamp value, you change clip 3, learning rate 2 to 0.02. What else can we do? Uh, we can try to, well, let me try something, equilibrium. Okay, I don't know. Hmm. Learning rate for equilibrium has a learning rate somewhere. So this was 2. The other one was, let me make this point smaller, v5 or 1, I don't know, 1.001. But we don't hit, wait, that's strange. We don't hit the debug for some reason we don't get here. Does it mean, okay, but still, I don't get why Mathematica says when we do, the graph says that we hit a zero somehow, somewhere. Oh, we don't actually, it's just 0.003, 0.003 onwards, 0.003, 0.003. So we never get to zero. But that's not what we want. We want something, what's the minimum value of this? Coherent is 72. That's good. The mean is 72. And then the medium, the minimum value is 0.03. Okay, it's still learning, but like it doesn't break down anyway, so we can try another thing because prediction is the one that has problems. Let's try another. Let's change prediction learning rate here as well. We already done another predict, anything predict. Turn this off. Orders. Okay, so when this is off, we don't really need. And then learning rate, we can make this one and maybe order to 3 to 2, and then project dimension. Nope, no change there. Anything else? Prediction learning rate in the genome. Okay, so the genome is just fine. I don't think we need to change anything there. Okay, that's it for predict. Let's try again. Okay. This is a crazy bug. I mean, I don't know. Once we solve this, we are starting to some serious training, and then we do we do something like build a CA for this. We will build a CA for from scratch for training. I mean, just write the entire grid and the rules and all that good stuff for this year. And then once we have an environment where we can train the the model, then we do some sort of merging the two. So we just need to figure out how to solve this bug. And are we doing good? Don't break. Do not break that hub. That works. Are you serious? Oh my God. That's so good. It's good to see it work. We're not getting to. Okay, let's see what the results are saying here. 32. How are we doing? Ah, look at that. Look at that. Look, it's looking good. Okay, things are looking good here. And it's not breaking down. Coherence is still up there. And what's the minimum, the maximum? So the minimum is 51. That's good. 0.51. And then medium is zero point 0.9. So we want to train this for, okay, we found the configuration that works. And looks like if we turn this, let's see, if I turn, let me turn something back on. This bandit is just like the bandit is how many, okay, let me just show you in the code how many agents, sorry, how many agents or what. Let me find it. It should be in the equilibrium. Bandit order. Bandit order. So if bandit order is on, it just means that every time the system, every time we train, the system tries to do some sort of uh, changing the dimension within the system as it trains. So when it's enabled, we create a new dimension, a new arm, that is, and then it just applies the predictors order to the system every time. So we get a new dimension every time we run the system, and this is when this is enabled, and then bandit order, then the state or the bandit total mod, the period equals to 0. We change the system like we are just updating the system in real time. So we turn that off and we turn it back on first and see what happened. So if I change this and turn it back on, what happens? Well, at least we know what's happening. So let's turn this. Let's turn bandit on so that the system keeps changing its dimensions every time. And do we want that in the real environment anyways? I don't know. Let's find out. So if this fails, then we know bandit apply is the culprit here. This function apply predictor order, it changes the system every time. So let's see what happens. Anyone text in chat? No chats? Questions? No questions? Yeah, okay. But this is just for 5,000 steps. We can try to go higher, like 20 steps, and see if it breaks towards the end of towards how many steps. I'm sure it will break. I don't know. Let's see. We just need so if this works, then oh, it doesn't work. So we know the problem. We know what's causing this. So every time we change the dimensions, something happens. So we don't want to change the state of the environment every time because this current like it gives the state a new sort of something to think about or to do, or a different kind of dimension or to to focus on, or I don't know the words to say that, but let's go to state and we will see what's that. So the state. Where is the state? Adaptive state. So this is the state, and this is the last summary. Bandit counts. Um, so equilibrium just changes stuff online whenever the system trains. Just keeps adapting the controller, just and it changes the knobs, the monitors, all the stuff that improves the system as it trains. And then we can see that the state is where's the state? It's supposed to be somewhere here. Okay, let's see where's the state. Oh yeah, it's not a parameter. It's just this all represents the state. Buffer, lambda energy, lambda spectral, previous theta, surprise. So we are changing all this stuff every time. So the values of this system changes. Um, what is the current is 0, starts with 0. Then every time we apply something, apply predictor order. So this is what happens. This is what does the change. If current arm is not equal to the new arm is selected from the bounded state. And I want to see if we can, have bandit predict order enabled and still solve the problem. Because right now we don't. This is when it's on. This happens. When it's off, when it's off, okay, when it's off, it does well. But let's try it for. It did well for 5,000. Let's try it for 20,000. And for this, I want to just not keep. Uh, Maybe we need to, but now let's try this 20,000. I don't know if these prints will eat up a lot of compute memory, but let's the no. I want to get some stuff up. Let's get this out. And false, false, false. And try again. So bandit is off. And what else is off? We reduce the learning rate. We change some parameter. It works for 5,000 steps. We want to see if it works for 20,000 steps. Oh, wait a minute. Wait a minute. The logs will be a lot, so I don't think we'll see the effect very well when we are logging every step. We need to log at every maybe 20 steps. Let's make it 20 so that we see clearly what's happening. And run again. Oh no. Damn it. Should be 5,000. Should be 20,000. Okay, this should be 32. Good. And this should be 20,000. Go. Okay. I don't know. Okay, are we any charts? No. Okay, we're streaming, but I don't know if connection is good or bad. Can't say. Closed captions. Okay. Still okay. We're still good. Let's change the video resolution. Current resolution. Da, da, da. Which is not supported. What? How about that? How am I supposed to change this YouTube? Okay. So we're still doing great. Okay, so let's clean this up first. The debug stuff. The PDB was in health. We had PDB here. We don't need this. We will need it when we get a bug. Maybe. Yeah. And another one is here. And then another one is doing okay, still good. Nothing is crazy, nothing is happening. So the previous results were good, were okay. Coherent, focused coherence is okay. Then the mean, it's also still up there. What is going crazy is health. Health is not so good. Stability also not so good. So many spikes. And pi is the attention. It's waving a lot. So much waves. Okay. All right. So let's see if it finished. Still doing great. Nothing crazy. We haven't hit our margin. Clip value is 3. So the system still learns. It doesn't break down. And we can make it 5 and see. No, 5. 5 will break the system, maybe. Maybe 5 will break the system. We should try to break it. Is this 3? This should be 3. I can turn this to 3. So far, so good. Okay, as this trains, let's go to CA and yeah, recursive adaptive algorithms that effectively updates parameter estimates in real time as new data arrives. That's what we're using. I think I mentioned this already. And yeah, squared filter. Least square filter is adaptive filter algorithm that recursively finds the coefficients that minimize the weighted linear list squares cost function relating to the input signals. Okay. Okay. What else? It's done. We're still okay. Coherent is zero point 0.8. No, this is realized. The actual. Oh, wait, what? Are you serious? No, you're not serious. Okay, you're not serious. This is 32. Let's run this. Oh my God, it's doing great. See this? This is what we want to see. We want to see coherent always. Look at pi. It's not so bad. Attention shifts all the time. And so these are the magic numbers. So coherent is 9.99. That's the mean. And medium is this. That's the minimum value we got. The minimum we got is what? Are you serious? No. The minimum we got is 9.99 in richer environment. Okay, so this guy is the bandit is the bug. I mean, we know the bug. We've already fixed the bug, but why can't we use bandit to? But why do we need to change the dimensions every time? Okay, let's ask GPT. GPT. This is about the dimensions. Dimensions. Where is the code? I need the code for that. Sure. Battery low. This one, equilibrium. Okay. I kind of feel that we should keep these, but we need a way to rewrite it. We maybe find a way to rewrite this function. Detached observation tensor. Okay, keep switching. Okay, why would so how do you recursive list square. Wait, so what? What so? Can check time. But okay, for 20 steps, we're doing great. I can try to go more than 20 steps, but let's not print stuff because get it's getting noisy. Health. Want to get these off. So we just do anything else? The kernel. And then equilibrium, did we have a print here? Nope. Okay, let's train this for 20 for 50 steps. Let's make this 33 and let's see what happens. 50 steps. Coherent is doing great. Realized, focused, realized, focused, realized, focused. Okay. Right. Yeah, this take a lot of time thinking, evaluating model performance with real-time updates. Sounds like model performance might be struggling because updating the dynamics in real time is interfering with its learning process. That's true. Just find out that, especially when the dimensions and weights change. The constant reset of state variables could be disrupting the learning stability, causing it to perform worse. Yes, when real-time updates are forced off, the model gets more time to adapt. Wait, what? When real-time are turned off, for the model gets more time to adapt, which might explain the better performance. Understanding potential cause for RLS model degradation with real-time updates, the user might be forcing issues due to real-time updates disrupting the model's learning, especially when the dimensionality and weights change. The constant updates could be preventing the model from properly converging to stable predictions. Yeah, and could have more time to adapt. Da, 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 and considering causes for RLS model instability with dimension changes could be struggling because it's sensitive to non-stationary Non. Okay. Is it? It says it's sensitive to non-stationary. What? Non-stationary. Non-stationary or misspecification. If dynamics keeps changing, it might adapt either too slowly or chase noise, which could be exacerbate that yeah exacerbate by mistuning. Additionally, dimension change may create issues if the model's parameter vector itself appropriately reinstantiate. Okay, what else are you thinking about? Evaluating the impact of frequent order changes and dynamic updates. Performance degradation is real-time updates, considering the model's performance will. Okay, investigating model will change dynamics. But yeah, so the first thoughts were interesting. The RL model might be struggling due to issues with dimension mismatch when the order changes. Oh, I see. That might be true or or not. If the model's reset function doesn't handle the updated dimensions properly, it could cause incorrect weight updates. Additionally, if the environment's dynamics are constantly changing, time varying A and C matrices, we have A and C in matrices. The real-time updates may disrupt the learning process rather than helping. Okay, so it just starts to think, explore, and we are 50%, and coherence hasn't gone to zero, still learning well, and we can do some pre graph plots. This is 33. So, yeah, this is 33. And how is it doing? Stability. Oh my God, the attention goes down. I mean, if attention's going down, this means the model is it's becoming confident enough, like things are great, not paying so much attention because the environment isn't bad, it's doing great. And yeah, these are good results anyways. But we need ChatGPT to answer these questions first. Why can't we update the environment in real time? Right? Can you change the dimensions? Can you change the weights? Is it a good idea to change the weights? No. Or good. Maybe it's good, maybe it's bad. Okay. Yeah, it's taking forever to think. Um, Uses of these. I misspelled square. Okay. Oh my God. I should check my prompts first. Okay. And finding and understanding apply. Yeah. Addressing reduction. Hmm. Okay. How is training going? We are not we are not that bad. Still okay. Let's see. Nice. It went up. Pi went up. Attention. Something happened. It started to pay so much attention. That's like when learning is happening. Like I want to understand this environment. The environment is crazy. I have to pay more attention. Then once it hits, it just goes. It once it gets to understand how the environment works, and then it just goes to stable. It relaxes, not paying so much attention because it's confident things are great, or you know it knows what's going on. Maybe that's what I my interpretation. But let's see. So what happened with chaos? Chaos is still up there, but remember, chaos doesn't really affect the system. It's a diagnostic of what the system is currently in. So the state of the system is chaotic, right? But that's weird because pi seems to just, go down and then relaxes, stays at the minimum. So because pi mean is oh, it's done. So yeah, we still good. So we start at 1.0. So we start at pi starts at 1, and once it starts at 1, it just goes up a few more steps, sticks there, then keeps dancing at around 2.5, then starts dropping towards 1, then goes to zero point 0.8, that just keeps dancing at the lower minimum. The minimum value is zero point 0.6. All right, so yeah, so these results needs better interpretation. We will do this with AI. Come on, man. How long are you taking to answer this question? 11 minutes. Hmm. Okay. Play I'm streaming the correct thing here. I don't know if I can see some. Okay. So it's still okay. It's doing fine. It hasn't gone crazy like we expect with uh with what we're asking LLM to answer, which is making it's taking long. Okay, it's fine. You can wait. How is energy? I want to see energy. Where is it? I don't have energy. Compression is also not bad. I want to see energy. Energy doesn't really. Oh, wait, this is the budget. Overshoots. It overshoots a lot. It overshoots a lot of time. Many steps. I don't know why I don't have energy here. Let's look at these. Yeah, so the mean of this energy is okay, 0.000002 the minimum. It goes to zero sometimes. Energy goes to zero and then come bounce back. Okay, so let's see why the graph. Where is the graph for energy? Do I have graph for energy? Yes, just before this we have this. Oh, I see. So energy is at the beginning we see a lot of usage of energy. This step there was a lot of usage. Then just goes below budget. So the budget is around this. I don't know what's the budget for this energy thing. Energy budget. Yeah, so this is point what? 0.000 something. 0.0001 or 2. Okay, it's below budget, so it only goes above budget a few steps, a few areas, and you can see that from this overshoot. So overshoots somewhere here. The overshoots will tell us when it goes above budget and when it's under budget. Yeah, so overshoots here, overshoots here, overshoots all these steps, overshoots here. Okay, how are you doing, chat? Okay, 15 minutes. Come on. Mm. Yeah, I like these results. I mean, I'm happy with these results. I think once we figure out what this LLM will tell us about this case. Okay, now we have the results. So short answer, the function isn't helping the learner. Okay. Should we accept this answer? I don't know. It's repeatedly rebooting it. If you keep changing dimensions or the dynamics, your RLS predictor spending its life in cold start land. I don't know what that means. So a frozen model can easily look better. Let's let's unpack. So it goes on to create the function. This does three things when the order changes. Sets order changes AR order, and then reset dimensions, observation dimensions, rebuilds W fast, W slow, covariance P is fast, P is slow, etc. With new shapes, copies over overlapping size of the old weights, covariance if shape overlaps. Otherwise, you effectively renit resets x previous and what x previous to. That's two steps previous to zero. So this function is not a gentle online update. It's a structural reset of the predictor whenever the bandit or tuner decides to change order. And in the kernel, you also do, yeah, that's true. So the changes in the observation dynamic dimensions also triggers a reset and set your history Zero your history. Okay. Combine those with your changing dynamics and things get spicy. Why this can make the online RLS worse than a frozen model? Okay, frozen model. So the cold start. You're constantly erasing the RLS memory. Uh, Reset dimension does roughly allocate fresh. Okay. Copy the overlapping block of old weights, covariance, prepare noise variance estimates. But that's happening only in no, actually, the equilibrium is applied on every environment. Okay, let's finish this and change order predictor, apply predictor order or chaos observation dynamics so that these changes triggers the kernel reset. You're repeatedly doing this. If you do this frequently, bandit period small, environment changing a lot, then the predictor never gets a long stretch of stationary data to converge. The bandit keeps trying new orders, each of which starts mostly untrained. The RLS update is always working in half-baked covariance and weights. A frozen model, by contrast, uses one fixed weight that and at least encodes some coherence mapping memory, that is, e.g., from your initial genome. Offline training isn't being continuously scrambled by resets and meta changes. So it's totally plausible for the static model to outperform the always adapting one simply because the adaptive one never gets this to stabilize. Oh, that's what we see on this. So it never gets to stabilize like this. It just keeps the model is it's always paying attention. It never gets to a stable state. So that's why you see from this pi, when you do training, we can see from the previous runs, an example of the previous run where pi just goes up and then stays up, never gets stable at all. Okay, not this one. Is it 31? No, no. I guess I deleted that. Yeah, but anyway, so stabilize. You are learning a moving target with a fast learner. Uh, yeah, or let's assume something like there's a slowly changing linear relationship between features phi x and target y. In your setup, the environment reacher dynamics A and readout C can drift switch sinusoidal random walks in YAML, and the AR order is being changed by bandit. Alana, the learning rate is non-trivial. Well, I changed this. Well, non-trivial. Set. Okay, we reset learning rate, by the way. So I think we do some sort of update to learning rate. Is it here or in the predictor? Yeah, so we do set learning rate for fast learner and slow learner. Don't forgetting factors. This is how fast to forget, and this is how slow to forget stuff from that. So the predictor is trying to chase non-stationary plant, changing A and C with changing architecture, order, different phi dimension, and aggressive forgetting, high learning rate, low lambda. Also, high learning rate, we forget a lot. That's a recipe for chasing noise. We're learning so much. The model is learning noise other than uh, the regime or the environment or what the environment looks like. Okay, so that's a recipe. Okay, so each regime change order change effectively invalidates the last batch of weights. RLSs happily walk away from previously good solution in the frozen model does not chase, it just stays at the average relationship it started with, which can look much better when the learner keeps overshooting. Feature mismatch when order and projection. Right. Does this preserve the semantics of the column? Okay, concrete things to check. It's about the order bandit. You don't need to answer. Oh, you don't need to answer anything. These are environments you can run straight in the code. Okay, so I think RLS on disable bandit, order bandit. I think I did this. Renit instead of partial reset. When you know things change a lot, you currently do this for big change in order dimension. It may actually be better to throw away all weights, just do re-init stuff. That ensures you don't reuse badly aligned weights. Columns slow down how often you change order. We I think we Oh, I see. So we just disabled it, not um, we do not change the value. The bandit can was it bandit predict? No. Which one is this? Period. The period is 3. Very fast. This is how often we change the order. With this, your order can change every few steps, which is a way too fast relative to how long RLS needs to judge another's quality. Try something like, okay, try learning of architecture on this update. Predict learning. Wait, we set it to 0. I think we set it to 0.01. Okay, so the big picture online recursive lists square is like a very eager student. If the teacher, the textbook, and the language are all change every few minutes, the student does worse than just sticking with the first decent textbook they saw. Uh, Resetting the predictor's internal state whenever the order or observation shape changes, zeroing the lagged. So the fact that your model performs better with this turned off is consistent with the system being over adaptive and under stable, not with the fundamental bad. Less being fundamentally bad. The way forward is to reduce how often you structurally change the model. Be more deliberate about when you reset versus warm start, forgetting learning rate for never new dynamics you are playing with. Once the learner isn't being rebooted all the time, online RLS should start to actually help instead of hurt. And we have seen that when we turn that the updates, we've seen the results. Now what we just need to figure out is I don't know, like environments change all the time. Like when we freeze the environment, or maybe we just need to change, like this the LLM suggested, we just need to change it differently, not every 3 steps. Every 3 steps is a lot. Like, even the environment we live in doesn't really change. I don't know. We don't really notice that, but every 3 steps is a lot. So maybe we can do more steps, like for 100 or 500 steps, and see how it performs. But yeah, so we know we can't really change an environment that often. We can change it, but how we change it is another factor. Okay, so um, in a frozen environment, and then moved to a non-stationary environment because we okay, we will be stationary. How do I stationary? We will be doing CA, and CA is another kind of environment. Let me just okay. So I guess this will take a lot of time. I think we can stop here, and we can continue tomorrow, where we will explore this idea of changing environments and why not change, like how to change an environment, because now we know how we change it and how it affects the learning of the model. But now we will explore maybe how well can we change it, what other ideas we can implement in the system, and we can use this to as a guide. So um, so today we solved the bug we had, and okay, clamping weight helped a lot because we set clip to 3. I think we can try 5 like tomorrow, and we can just try changing these values until we get to a, a better state. Because now I don't know, maybe it does perform better, but is that like, are we sure it's doing great? I mean, like, do we have to change some things? I will train this for another 2,000, 200,000, and see if the model gets better at some point, or gets worse at some point. So I'll do this to 2,000, 200,000, 200K steps, and then change this to these. I will leave this to train for those many steps. Okay, so tomorrow we will see these results, and then we will explore different ideas and how to change this. And then we can also explore these LLMs ideas, like changing the environment and not changing the environment, and how does changing the environment, we have seen how it affects the system, but how how can we make it so that changing the environment can also make the system uh, do better or learn better or something like that. So that's what we'll explore next. So thank you for those who are watching. Let me see charts now. Charts, great. Uh, yeah. So thank you for tuning in, and um, if you haven't watched the previous videos, you can go to the channel. Then there is a playlist called Life Science. those are everything we are doing will be going to that playlist. So you can revisit all the streams that you haven't really watched and see the steps because it is systematic. We are going step by step building this thing up, and finally once we have a stable enough system because uh, in an environment, then we can try to build cellular automata that can this like this will be the controller for the CAs. So CAs think game of life. Then if you think game of life, they are running on rules. But imagine if we gave these creatures in a CA some sort of a controller or something like that. Like what will happen to such a system. So that's the end goal. But for now, we're just going step by step. So those who haven't watched, if you haven't watched the previous videos, you can do so in the playlist Life Science. So with that, thank you for watching and see you next time. Uh, Training. Okay.